In today's video, we'll be talking about electric fields. After watching this video, you should be able to explain how an electric field is created, be able to determine the strength of an electric field, and then be able to calculate the force on a test charge in an electric field. So let's get right into the fun. Electric fields are action at a distance forces. Basically what that means is they do not need to touch. So it's not like a baseball bat hitting a ball. Clearly the bat and the ball touch one another. Or say you rubbing your hand on a rug, causing friction to be created. Again, that is not action at a distance. Instead, electric fields, they actually do not need to be touching one another. You can experience an electric field without direct contact. Another great example of this would be gravity is an action at a distance force. Okay, we know that if you jump out of a plane, you're going to start to fall towards Earth, and that's gravity pulling you down towards the Earth. And sometimes when I'll explain electric fields, I like to use a baked cookies analogy. I don't know if any of you guys have ever had this happen before, but I have been taking naps, and back when I was a kid, and my mom would be baking cookies, and I would actually wake up from my nap smelling those cookies, and I would run down to the kitchen to be able to get a hot cookie. Well, the same idea happens with electric fields. Basically, the smell of the cookies is kind of like an electric field where it's pulling me in towards those cookies. An electric field can do the same thing depending on the charges involved. An electric field can pull a particle in. Okay, and so and also something else that's kind of useful with the baked cookies analogy is as you get closer to the cookies, the smell becomes more and more intense. It smells more and more like cookies. The same is true of an electric field. As you get closer to the charge creating the electric field, the intensity of that field increases, and as you're further away from it, the field decreases. And the same would be true of gravity, right? We know that as you get further and further away from the surface of the Earth, gravity continues to decrease and decrease until basically you aren't experiencing the Earth's gravity anymore, and you're now in outer space. Okay, so electric fields are an action at a distance force. So like I said, electric fields work very similar to gravitational fields. The big difference between gravitational fields and electric fields is gravitational fields are always attractive. And what that means is basically if I'm here jumping out of a plane, I'm always going to fall down towards the Earth. The Earth will never push me away. Okay, so I'm always attracted to the Earth, and that's always going to be true of gravitational fields. Electric fields, how they're different is that they can either be attractive or repulsive depending upon the combination of charges involved. So I mean, for instance, let's say I say the Earth is a positively charged particle, and I make this little sphere right here positively charged. Clearly these two are not going to attract one another. Instead, they're actually going to repel. So this is going to be pushing this charge away. Okay, and that is the big difference between a gravitational field and an electric field. So what the heck is an electric field? I guess that was a good question to ask. An electric field, which is typically represented by a capital E, is a vector quantity. And so what that means is it has a magnitude to it and a direction associated with it. The directional piece on electric fields, I highly recommend just using common sense. Okay, so if you know that a negative charge is creating an electric field and you have a positive charge in this electric field, well, the positive is going to be attracted to the negative. So if you just use common sense and those rules of basically attraction and repulsion based upon the charges, you've got the directional piece done. Then all you're left with is trying to calculate the magnitude of the electric field. The units of electric field are newtons per coulomb. Okay, and I highly recommend kind of making a note as to what these units actually are telling you. Okay, let's say I have a electric field of 3 Newton coulombs. Okay, what is that actually saying? All right, what is that telling you? Basically, what it's saying is if you have a 1 coulomb charge in this 3 Newton coulomb electric field, it will feel a force of 3 newtons, because if you do the math here, 3 Newton coulombs, and if you want, you can put a 1 there. For every coulomb, it's going to feel 3 newtons of force, because basically 1 coulomb, the coulombs cancel, and what's left is 3. right, and newtons. So it would feel 3 newtons of force. And that's what this number is telling you. It's telling you 3 newtons per every 1 coulomb of charge. So just for fun, what if I had a 2 coulomb charge in this electric field? Okay, let's say I drop a 2 coulomb charge into this 3 newton coulomb electric field. What would the force be? Well, if a 1 coulomb charge feels 3 newtons, this one, a 2 coulomb one, would feel 6 newtons. It would be double. Okay. What about if I drop a 3 coulomb charge in this electric field? Well, a 1 coulomb was 3 newtons, a 2 coulomb was 6 newtons, and then a 3 coulomb would have to be 9 newtons. Okay, and again, I really think those units are useful in terms of telling you what an electric field really means. It's a way of saying this is how many newtons of force a charge would feel in this electric field per coulomb. Okay. Now, what actually creates an electric field? An electric field is created from a source charge, okay? And I wish I had a better name than that, but it's this charge that creates an electric field. And throughout this whole lesson, I'm going to be referring to the source charge as big Q. Okay, so big Q is going to always be the one creating an electric field. Okay, and if you want, I mean, like you can kind of just imagine a series Q, and basically it's creating an electric field, and we'll represent this by lines. Okay, so there is an electric field, and when I'm saying I'm putting a test charge in it, I could be putting like a little charge here into this field, and I'm just wondering, what is it experiencing? What type of force does it experience? Okay, the test charge will always be, in these notes anyway, called little q. Okay, so big Q creates the field, little q is the test charge. It's like the little test pilot that's going to go into the electric field and see if it can, what type of force it experiences from that electric field. So it can test how strong big Q is. And also we can kind of figure out the intensity of that electric field. Okay, so the test charge does exactly that. It tests the intensity of the electric field of big Q. So here is a picture of a negatively charged particle, and that is big Q right there. Okay, and it's making an electric field. And here is little q right here. Okay, and that's little q, big Q. An electron's electric field strength is calculated with this formula, E equals F over Q. I'm going to scribble that little e out. So E equals F over little q. Okay, and again, the units are newtons per coulomb. Okay, so this is the formula that we're going to be using to calculate either the intensity of the electric field, because that would be E, or you could calculate the force on little q, or you can figure out the charge of little q if you need to. The big thing that I want to make clear is that, and areas where students will make mistakes, is the charge here, this little q, is the charge on little q. It is the charge on little q, not big Q. So if I were writing notes, this would be something I'd put a star next to. This formula uses little q, not big Q. So this is how many coulombs are on this guy right here. How many coulombs are on little q? Okay, for that formula. So let's do an example problem here. It says, calculate the magnitude of force that a proton will experience if it is placed at a point in an electric field where the intensity is 0.15 newtons per coulomb. And just so you guys know, a proton has a charge of 1.6 times 10 to the negative 19th coulombs. Okay, so if you use the formula that we just talked about in the previous slide, it is E equals F over little q, okay, and that is the charge on the little test charge that you're putting into this electric field. Okay, so they tell us that the intensity of the field is 0.15 newtons per coulomb, and that is big E. Okay, so 0.15 newtons per coulomb, and the test charge is a charge of 1.6 times 10 to the negative 19th. So that's little q, 1.6 times 10 to the negative 19th coulombs. I'm wondering what type of force that charge would be feeling in this electric field. Okay, so I'm just going to be plugging these numbers into this equation. And so what I would have is 0.15 Newton coulombs is equal to F over 1.6 times 10 to the negative 19th coulombs. Okay? And if you just basically cross multiply here, you would find out that the force equals 2.4 times 10 to the negative 20th newtons. Okay, is that a big force? Absolutely not, right? It's a very small force, but that kind of makes sense. I mean, this is just one proton in an electric field, okay? So it shouldn't be like a massive force. But that would be what the force or the magnitude of the force that proton would be experiencing in this electric field. Okay. So far, if you will, what we have talked about is we've talked about the electric field, okay, which is represented by a big E. And we've been talking about how that electric field has an effect on little q. And the formula that we have been using to find out that effect is E equals F over little q. Okay, so this is kind of a little flow chart I'm just going to make right now. Okay, so big E, the electric field has an effect on a test charge. Okay, this is my test charge here, little q. What makes big E? Well, if you remember from the previous slide or two, we said that big Q, the charge on big Q, is what's responsible actually for making the electric field, okay? So I'm wondering, how can we figure out what determines the magnitude of the electric field? Is there any equation that would be involving big Q? And believe it or not, this equation right here, that F, the force, is actually Coulomb's law. So I'm going to just rewrite that equation right here. F over little q. But what I'm going to do is I'm going to insert Coulomb's law where it says F. I remember Coulomb's law is F equals K times, and I'm going to use big Q here, times little q over d squared. Okay, that's Coulomb's law. So I'm going to insert that piece into this right here. So it would look something like this. Big E equals K times big Q times little q over d squared over little q. And one thing you may notice right away is that I can cancel these little q's. Okay? And so you get this new formula. Let me just change colors so that we can make it more exciting. You get this new formula, and this is kind of an important one for you to remember. Big E equals K times big Q over d squared. Okay, and that is now, notice what's changed from, say, this formula over here and this formula here. Well, that is the charge on little q. Okay, whereas this is the charge on big Q. And you can quickly see how students can mess this up and be using the wrong charge for various problems. Okay, and that'll get you the wrong answer basically. So make sure you take extra care to figure out what is it that you're trying to find. Are you trying to find the force on a test charge? If that's the case, you probably want to use this formula. Are you trying to find out what the magnitude of the electric field being created is? If that's the case, you might want to use this formula, because I might tell you that a charge of 3 coulombs is creating an electric field, and it's a distance of 2 meters away. What would the electric field be at that point? Well, then you'd want to use this formula right here. Okay. So just take extra care when you're solving problems, and I think you'll be just fine. So again, just to put the previous slide into kind of some sort of text in terms of knowing which formula to use, make sure you read the problem carefully. Are they giving you information about the test charge, which would be little q? Are they telling you information about the charge creating the electric field, and so that would be big Q? I mean, those are big hints in terms of telling you which formula you want to use. So kind of keep that all in mind. And other hints would be like, is the problem asking about the force felt by a test charge? If they're asking about the force felt by a test charge, well then you have to use the equation that actually has force in it, right? If you use the other equation, then you're not going to be able to calculate force. So just kind of keep those things in mind as you work through the problems. So let's do an example problem real quickly here. What is the magnitude of the electric field intensity at a point where a proton experiences an electrostatic force of magnitude 2.3 times 10 to the negative 25th newtons? A proton has a charge of 1.6 times 10 to the negative 19th. Okay, so which formula do I want to use? Well, I'm trying to find the magnitude of the electric field, right? But I only know that I have a proton, so that's my test charge, and it's experiencing a force of 2.3 times 10 to the negative 25th newtons. Right. So what I would probably be doing is I would probably want to use this equation, E equals F over little q. And the reason why I'm doing that one is if I use, say, this equation, E equals K times big Q over D squared, well, right away you should notice a few things are missing. One, I do not know the charge on big Q. I don't know what type of charge is making this electric field. I also don't know any distances, so I'd have a really hard time of calculating E, right? The only thing I know in this equation so far would be K. Whereas in this equation, I certainly can calculate big E because I know the force, right? It tells me it right there. And I know the charge on the test charge because a proton has a charge of 1.6 times 10 to the negative 19th, and that should say coulombs. I apologize, I forgot to put the units there. So let's go through this and find out what the magnitude of the electric field would be. All right, so I'm going to use this equation right here, and my force is 2.3 times 10 to the negative 25th newtons over a charge of 1.6 times 10 to the negative 19th coulombs. Okay? And if you do that math, you would get a E of 1.44 times 10 to the negative 6th Newton coulombs. All right, that is the magnitude of the electric field being created, okay, by using that formula. So that should take care of today's video. I will see you guys next time.